Good morning, Algebra 2. We're going to get started with section 6.7 notes, which is going to be about inverse functions. So first we're going to talk about inverse relations. Inverse relations are expressions that completely undo, quote unquote, undo each other. Okay, so the notation for this is the inverse of f of, let's just make that look like an f, of f of x is f to the -1 of x. Okay, now we say this f to the -1 of x, we say the inverse of f. Okay, so that's how we rewrite it. That's the notation. Know it, love it, learn it. Okay, so some examples of what inverses are. Hopefully we all know this. If we have x plus 2 minus 2, this is equal to x. So addition and subtraction are inverses of each other. If we have 2x over 2, okay, this gives us x. So multiplication, 2 times x, division, this fraction means dividing, these are opposites of each other. So this is equal to x. So multiplication and division are opposites of each other, are inverses of each other. Now for the tough one. If we have the square root of x squared, this is equal to x, because squares and square roots are inverses of each other. Okay? Know all three of these, love all three of these. You're going to need to know them for your homework tonight. So let's get started on what it is to be to an inverse. So between any two inverse relationships, the x and y are exchanged, inverse operations are used, and f of the inverse of f equals x, as well as the inverse of f of x is equal to x. So this is using function composition of functions. This is what we learned in our last lesson. So what happens is if they are two inverse relations, you have to have both. Both of these must work out. Okay, so a little love note on the side here is you must have, and I'm going to double underline that word must have both function compositions work. Are both function compositions equal to x for them to be inverses? Okay, super importante. So must have both. Must have both. Oh my gosh, you must have both. So for our examples, are the two functions inverses? Yes or no? And you have to prove your answer using composition of functions. So we have f of x is equal to 2x plus 3. We have g of x is equal to x minus 3 over 2. I am a fog person. I like to start with f of g. So we have f of g of x. Okay. I'm going to rewrite my g of x expression in here, which is x minus 3. So we have f of x minus 3 over 2. So if we have f of this expression, that means we're replacing the x in our f of x equation with this expression. So we have 2, and then the x is right next to that 2, so we have 2 times x minus 3 over 2 plus 3. That's how you rewrite that. If you don't remember, you can always rewatch the last video. Okay, so we're going to get started. So we have a fraction of a 2 at the bottom and then a 2 up top. These are going to cancel out. Okay, this big 2 and this 2 in the fraction cancel each other out. So we're left with x minus 3. We can drop the parentheses, plus 3. Now, the minus 3 and the plus 3 cancel each other out. So we're only left with this equaling to x. Now, I said that both have to equal to x. So you can't just do f of g of x. You have to do both. So you have to do the other one too, which is g of f of x. Okay, you have to do both. You have to do both in order to prove that they are inverses. Because one might work, but the other one might not. So we have g of f of x. So we have g of 2x plus 3, because that's what f of x equals. So that means in our equation here, we're replacing this little x up top with all of this stuff, this 2x plus 3. So when I rewrite this, I get 2x plus 3, replacing that x, and then we have a minus 3 over 2. Now, nothing's being multiplied to this 2x plus 3, so I can drop the parentheses, and I have 2x plus 3 minus 3 over 2. Now, I can't divide by 2 yet because not all of these pieces are divisible by 2. So let's see what happens. We have a plus 3 and we have a minus 3. They cancel each other out. So that means we're left with 2x over 2. Now, both of those are divisible by 2 and they cancel each other out. That's another way to think about it. So we're left with this equation, this composition equals x. So looking at my blue composition and my green composition, do they both equal to x? Because that's what we need to say that they're inverses. They do. So our answer is a big resounding yes. They are inverses of each other. Now let's look at number 2. We have f of x is equal to x squared plus 2, and g of x is equal to the square root of x plus 2. So again, I'm a f of g person. I always like to start with f of g. So I have f of g of x. And I'm going to zoom in a little bit here. So my g of x, I rewrite inside. So I have the square root of x plus 2. F is equal to the square root of x plus 2. So that means I'm going to replace my x in my f of x equation with the square root of x plus 2. So parentheses, square root of x plus 2, all of that squared, and then a plus 2 on the outside. So again, I just replaced this x with g of x, what g of x equals. So that's how I got the quantity of the square root of x plus 2 squared. Now, squares and square roots, do they cancel each other out? Yes, they do. So we're left with a parentheses, x plus 2 plus 2. Is anything being multiplied to this parentheses? No. So we can drop it. So we have x plus 2 plus 2. Now, when we combine like terms here, we get x plus 4. Is this equal to x? It is not equal to x. Okay, this fails. Okay, it equals x plus 4. So a little love note for yourself. If one fails, if one of your function composition fails, meaning it doesn't equal x, then stop. Because both need to work, okay? If one doesn't work, the whole thing is a no-go. So the big resounding no. Okay, if one doesn't work, none of them work. All right, for examples 3 and 4, now we're going to find the inverse of each of these. Okay, so if we have f of x, the strategy we're going to use is to switch the x and y and then solve for our y. So for number 3, if we have f of x is equal to 2x plus 3, remember f of x is just a fancy mathematician way to write an equation like y is equal to 2x plus 3. Okay, so if you see f of x, just replace it with a y so you can find the inverse. Okay, so our strategy is to switch our x and y. So I'm going to do this in a different color. I'm feeling the orange today. So we're going to switch x and y's place. So now we have x is equal to 2y plus 3. And now we're going to solve for our y. So we subtract 3 on both sides. We get x minus 3 is equal to 2y. To get that y by itself now, we divide by 2 on both sides. So we get x minus 3 over 2 is equal to y. This means that our inverse of f, and remember, we have to write f to the negative 1 for the inverse is equal to x minus 3 over 2. And that is your final answer. Oop, let me make that go all the way. All right. Moving on. Number 4. We have f of x is equal to x squared plus 5. So again, we're going to rewrite this with a y. So that means we drop this f of x and replace it with a y. So we get y is equal to x squared plus 5. Now what we have to do is we have to flip-flop the locations of our x and our y. So we get x is equal to y squared plus 5. Okay, first step is to subtract 5 on both sides. So we get x minus 5 is equal to y squared. Now, the opposite or the inverse of a square is a square root. So we're going to square root x minus 5, and we're going to square root y squared. Now remember, squares and square roots cancel each other out. So what we're left with is plus or minus, because we square rooted on both sides of the equal sign, you gotta remember it, I know it's your favorite thing, plus or minus the square root of x minus 5 is equal to y. This means that the inverse of f is equal to plus or minus the square root of x minus 5. That is our final answer. Remember to write it in inverse notation. Moving on to the next examples with graphing. So you're going to graph the relations given, and you're going to determine if it's a function. Then you're going to find the inverse of its relation or of the equation, graph its inverse, and then also decide if it's a function. Now, one thing you should know is that all inverse graphs, if they're inverses of each other, are symmetrical. Over the diagonal of y equals x. So they're all symmetrical. They all are going to be, if they don't look symmetrical, something went horribly wrong. Okay, so looking at the first one here, we have a table of values that we are going to graph on our coordinate plane here. So we have this coordinate, and I'm going to do this in green. So you're going to graph it. You're going to plot the dots. So we have negative 1, 1. We have 0, 2. We have 1, 3. And we have 1, 4. Okay, now we're going to look to see if this is a function. So to see if something's a function on a graph, you have to use the vertical line test, okay? So looking here, if you can see my little arrow thing, does this pass my vertical line test? Does this only have one dot passing through at this point on the x-axis? No, there's 2 points. So the answer is no, it's not a function because it doesn't pass the vertical line test, which from here on out I'm going to abbreviate VLT because I'm lazy and I don't like writing. Okay, now we need to figure out the inverse. So how do we write the inverse from a table? All you do, and this is super easy peasy, is you switch x and y values. So for this first one, if my x was negative 1 and my y was 1, I flip-flop. My x is going to be 1, my y is going to be negative 1. And you can do the same thing all the way through. So we have 2 up top, 0 at the bottom, 3 up top, 1 at the bottom, 4 up top, 1 at the bottom. And now we're going to graph to see if it is a function or not. So we have 1, negative 1. We have 2, 0. We have 3, 1, and we have 4, 1. So using my vertical line test on these dots, does each vertical line have a single dot for the purple function? It sure does, so it is a function. Okay, it passes the vertical line test. Woohoo! All right, so that's the first way to find an inverse when graphing. Now let's look on to the second one. We have y is equal to 2x plus 6. Okay, so you have to remember how to graph this. So let's do this in a fun color. I'm feeling orange. So we have to remember y is equal to mx plus b. Oh, it's back forever. Our m for this function is 2, but remember we have to write it as a fraction, so it's going to be 2 over 1, which means our b is equal to 6. Now, where do we begin with this equation? Do we start with the m or do we start with the b? We start with the b, which is equal to 6 on the y-axis. You always begin on the y-axis. Then we rise 2 over 1 and rise 2 over 1. If you can't do that, if you can't go any further, you go back to your original point and you do the opposite. If you go up 1, right 1, you're going to go down to, if you're going to go up 2, right 1, you're going to go down 2, left 1. And you're going to do that all the way until you can't do it no more. I'm not going to talk about each one because you guys can handle this. I'm going to draw my line. Okay, now we're going to determine if it's a function. Is it a function? If I use my vertical line test, is it only hitting my line once the whole time? Yes. Yes, it is. All linear equations are functions, okay? Every single one. Now we have to find the inverse, okay? So we're going to find the inverse. So I'm going to take this equation we're given. I'm going to flip-flop the x and y. So we have x is equal to 2y plus 6, and you're going to solve for your y. Subtract 6 on both sides, we get x minus 6 is equal to 2y. Divide by 2 on both sides, we get x minus 6 over 2 is equal to y. Now, you can write this as f of x is equal to x minus 6 over 2. Oops, what did Miss R forget? She forgot her inverse notation. F inverse of x is equal to x minus 6 over 2. Or, in order to graph it, we have to rewrite it as the inverse of f of x is equal to, there's technically a 1 in front of here, so you're going to split this up into two fractions. You get 1/2 x, right, because there's a 1 in front of this x, so 1 over 2, 1/2, minus 6 divided by 2, 3. So my m for this one is going to be 1/2. My b is going to be -3. So now I'm going to graph. And I'm not going to go over all of it. You guys can handle it. So this is what our graph should look like. Now we have to determine if it's a function. So using our vertical line test all the way across this blue graph, does it ever hit the blue graph more than once? It doesn't, so that means it is a function. It does pass the vertical line test. All right, moving on. We're going to go to example 3. So now we have y is equal to x squared plus 3. Done, done, done. So I'm going to do this one in pink. So first thing you're going to do is you're going to make an XY table. Okay, and you're going to type this function into your calculator. Okay, so when you type this function into your calculator, you're going to go to the y equals button on the top left, and you're going to type in x squared plus 3. After you type in x squared plus 3, you're going to hit the blue second button, and then you're going to hit the graph button, and a table should pop up. Now, for your table that you are going to write out, you're going to use the values from -2 to 2. So we're going to have -2, -1, 0, 1, 2. So on your calculator, for -2, to find -2, scroll up, okay, using your directional pad. So you should have a 7, a 4, a 3, a 4, and a 7 for these values. And now what you're going to do is you're going to graph it. You're going to plot your dots. Now this is what your graph should look like. So now we have to determine, is this a function or not? Okay, so using our vertical line test, will this graph or hit the vertical line more than once at any point? No, it will not. So that means that yes, because it passes the vertical line test. Okay, it is a function. Now, what you need to know is, or what you need to remember is quadratics are parabolas, which pass the vertical line test. Like linears, parabolas or quadratics pass the vertical line test. Okay, now enough about the original function. Let's talk about the inverse. So we're going to flip-flop our x and y. So we get x is equal to y squared plus 3. And now we're going to solve for our y. I've got baby colors happening here, light pink and light blue. So we get x minus 3 is equal to y squared. And then we have to square root on both sides. And remember, when we square root on both sides, we get plus or minus. The square root of x minus 3 is equal to y. So the inverse of this is f to the negative 1 is equal to plus or minus the square root of x minus 3. Now, here's the nice thing about parabolas is you are going to make an xy table, and you're going to flip-flop your values from your pink function, from your pink xy table. So we have 7, negative 2. We have 4, negative 1. We have 3, 0. 4, 1. 2, 7. All right. So now we're going to plot the blue table on our graph, and you can do that on your own. All right. You should have a graph that looks like this blue one here. So we have to determine if this is a function. Does it pass my vertical line test? Is it always only hitting one point of the graph? No, for a lot of it, it's hitting 2 points all the time here. So the answer is going to be no. It doesn't pass the vertical line test. And I'm going to circle my inverse answer. Okay, so your homework for tonight is that 6.7 worksheet, which is going to be attached in your Google Classroom because I don't believe it's part of your packet that I gave you. And then you have an extra credit opportunity, page 282, numbers 29, 49 through 50, 55 through 58. Now, if you are going to do the extra credit, just upload it with your homework answers, okay? If you have any questions, always rewatch the video, or you can email me with questions. Have a wonderful day until next time.